All right, well, thank you very much. It's my first time in Spain, so thank you all for having me here. I probably didn't bring a strong enough SPF sunscreen, but, you know, we'll make do with it. So today we're going to be talking about Akka.NET and the future of distributed programming in .NET. Now, quick show of hands. Who in the room is a .NET developer primarily? All right, there we go. And who does something else like JavaScript or Java, Scala? Quick show of hands. All right, cool, so about half and half. Well, regardless of what your programming language is, there's not that much .NET stuff that's actually in this talk. It's mostly about the actor model and about where you might want to use it in the context of developing sort of modern back-end applications. So one of the industry trends that has sort of brought the actor model out of obscurity and made it kind of a mainstream technology that you're hearing a lot about at conferences like this and seeing more and more articles about online is that expectations for back-end developers have grown a lot over the past 5 to 10 years. And there's a lot of different factors at work that are driving that. The first big one is the concept of being always on, being available at all times. Quick show of hands, how many of you would use Google if it went down for maintenance 1 day a week? You wouldn't, right? Or what about your bank or any other piece of software or service you consider to be critical to your day-to-day life? Downtime isn't tolerated anymore. It's not 1996. So you're expected to basically develop applications that can stay up, they can be upgraded without maintenance windows, etc. So that's one really big expectation. But then on top of that, you also can't go down by accident. You are expected to design systems that are resilient to all different classes of failure, including hardware failing, etc. And so this is another set of expectations that backend developers are expected to shoulder by their customers and by their companies that employ them. The next big trend is the increasing velocity of data that we're expected to retain and use and turn into some sort of business value for both our companies and our customers as well. So in order to reason about this data and manage it and put it to use, some of the tools that we were able to use in sort of traditional stateless CRUD architectures will be put under immense amounts of stress. And I'm going to show you some examples of that in the next couple of slides. Another big factor that's driving these heightened expectations is the increasing variety of experiences we're expected to support. The iPhone just celebrated its 10th anniversary this year. That was a class of consumer computing that we never had to support before, this sort of rich internet-enabled phone. Well, now we're also expected to build things like web APIs, or being able to support real-time web applications where we're using WebSockets to go and communicate back and forth. Now we're also connecting to other types of embedded devices. This is what the whole IoT field is about. So we're expected to be able to support a much larger range of experiences for different clients of our systems than we had to. So all of these different forces are all sort of arriving at around the same time, and the net result of it is that we have to develop a way to scale our applications to support all of these requirements at once. And here's the bad news, and this is probably why you're at this conference. All the obvious ways of achieving that are wrong. Let me give you some examples. So this is what my view of a traditional enterprise application looks like from inception. You have a load balancer, some web servers, and then you have your private zone, where you have a relational database with a failover or two behind it. Then maybe you have a couple of internal line of business applications for doing administrative functions, reporting, business intelligence, that all consume to maybe an OLAP cube for running reports and analytics, etc. And this has more or less been what the standard architecture has looked like for the past 25 years of sort of application development. Would all of you agree? Yeah. This is sort of a pretty safe default that a lot of companies have adopted over the years. Well, what happens when one of these scaling pressures gets applied to this system? Let's say we have a big surge in user activities, so an increase in volume and variety, perhaps. Where is the stress going to be applied on this system first? It's going to be our relational database, right? All the arrows are pointing towards it. And in .NET land, what this looks like in a day-to-day basis for us is SQL Server contention pressure and things like that, where you have a lot of lock escalation time eating up your CPU and slowing down your system. Well, the obvious solution to this problem is rather than having just one writable master, we're going to shard it. We're going to go ahead and take our data and federate it into multiple evenly distributed partitions, right? This is this is like SQL Server federations is one approach to this, and every relational database technology has their own sort of equivalent to that. We go ahead and have our clients talk to this coordinator, and then we go ahead and distribute requests along these shards. All right. Well, this is a pretty state-of-the-art solution as of 2003, 2004, 2005, sort of in that range. But as really big companies, some of the first big .com giants like Amazon discovered, this is a brittle solution for a couple of reasons. First, what happens when a master goes down in this scenario? What needs to take place in order for transactions to continue being processed? One of the slaves has to be elected to become a new master, right? And during that period of time when there's no master elected for that shard, you have downtime. So by default, this model has downtime built into it as a feature of how it works. But there's a more insidious problem, which is what occurs if there's a network partition that separates these masters from their slaves? Well, these systems weren't really designed with the concept of network topology in mind. And what would occur is a very nasty type of distributed programming problem called a split brain, where you have two different masters in the system, both trying to act authoritatively about what the current consistent state of the system is. So this solution breaks down as soon as the network stops behaving perfectly. And one of the rules of distributed computing is the network is never perfect. I told an anecdote to a couple of folks at one of the speakers events last night about a raccoon chewing through a power cable and bringing down a data center that way. That's, things can happen. So there's all sorts of different events that can cause a network partition, and they should be treated as an inevitability. So that's one type of scenario where the obvious solution fails. Another one. Suppose you have to support real-time user interactivity as a new requirement. So in my previous job, before I started working on Akka.NET full-time, I had to build a marketing automation system. And the way those typically work is you define a set of business rules for who should receive an ad or who should receive an email or an offer of some sort. And you wait to see each of the different users who are touching the various customer touch points you're integrated into. You want to wait to see if a user's produced a set of events. Let's say it's events 0 through 3 in this instance. If they've produced all 4 of these events, we go ahead and send some type of reaction back to the user, whether it's displaying an ad, sending an offer, showing a discount. Doesn't really matter what the event is. What's important is that we do this quickly, within a second, or preferably under a second if you can. But if the user hasn't produced these events, we want to wait and observe what the user's stream of activity is before reacting to it. Well, how would you implement this type of system using the CRUD architecture I showed you in the previous diagram? Well, the obvious solution here is a technique known as read after write. Well, let's suppose the user produces all 4 of their events. The first event gets propagated from the load balancer down to one of our web servers, and then passed along to the data tier. So we go ahead and write that event. Then we read back what are all the other events in this range for this user, and we get back the previous event that we had written. Well, as the system progresses, eventually you'll start getting back the set of all the previous events that you've written. At the very end, you should get all 4 of the events you're looking for, and you go ahead and send this message back to the end user. So this is sort of theoretically how read after write should work in a real-time streaming scenario. Well, having tried to implement this in production, let me show you what actually happens. An event comes in, and another event comes in at the same time. Neither of them have been written. We go ahead and we start performing writes against our database, and we get totally unpredictable results back. in terms of what's actually being written at any given time. And this is due largely in part to the fact that no matter how strongly consistent your database is, it can't guarantee the concurrency or the event order of what's happening at the layer above it in the application, particularly if you're using a distributed database like I was at the time, using Cassandra, which has its own distribution problems. And the end result is you just get frustration and a system that doesn't work very well. So the point of all of this is that in order for us to tackle these types of scaling challenges, we have to look at non-obvious solutions and add new tools to our repertoire so we can go ahead and address these problems effectively and deliver solutions that match our customers' expectations. And this is the field of distributed programming. My hypothesis is that distributed programming is going to be something that every developer knows how to do over the course of the next 10 years, until quantum computing invalidates it, in case you attended the keynote this morning. So things you need to know in order to do distributed programming. The first is the concept of statefulness, the ability to manage your own state and not outsource everything to a database. That's one of the first sort of little principles we have to learn. Next, concurrency. Distributed systems are by their very nature concurrent. There's going to be activity happening across multiple different physical nodes in the network, and we need to come up with a model that allows us to reconcile that consistently with our business rules and our state. Topology and discovery. So topology in this case means all of the different nodes in your network being aware of each other and being able to address, communicate, and contact each other as well. So for instance, in your standard sort of stateless CRUD environment, do any of the web servers know about the presence of any of the other web servers? No, they have no awareness of the topology at all. This is one of the things we have to introduce to build a distributed system, though, is awareness of who are the other nodes in your network and what are they capable of doing. Recovering from failure. So network failures are inevitable. Therefore, we have to design our applications in the anticipation of an eventual failure occurring on the network somewhere. We just have to build it into how our applications work by design from day one. And lastly, we have issues like bottlenecks and consistency. What I'm going to talk about today, unavailability too. What I'm going to talk about today is some distributed programming concepts and how the actor model gives programmers access to be able to express these ideas very simply using code that's relatively understandable and easy to write and debug. So the first concept we're going to take a look at is the notion of a stateful application. What happens when your application itself is the single source of truth for your state and your database changes its role to just being cold storage, a place where you go to recover state once you need it, and a place to store it so you make sure you don't lose it in the event of a crash. Next is protocol-driven design, the idea of designing a flow of behavior through your system that anticipates things like network failures and other types of issues that may occur. How do you go ahead and build that into a reproducible unit you can use over and over again? Next is fault and resource isolation. A term that's been thrown around a lot at this conference is microservices. And that's essentially one of the things that principle is trying to achieve, is the ability to go ahead and isolate different services from each other physically, so something like a hardware failure can't create total unavailability of your service. So how do you think about things in that sort of that manner? And then next, we have the notion of decentralized architectures. The primary reason for bottlenecks in a lot of these systems is there's one node responsible for some big piece of the system at any given time. And you intrinsically can't scale that without decentralizing it. So that's another thing we're going to take a look at. And lastly is the CAP theorem. Quick show of hands, who's familiar with the CAP theorem already? All right, so a handful, good. Well, this will be new information, and this will give you some language for being able to talk objectively about trade-offs you should be making when you design a distributed system. And we'll get more into that in a moment. Now, the actor model is one of the programmatic techniques we can use for reasoning about all these different distributed programming concerns. Now, this is Fabio, and he is the mascot of the actor model as far as I'm concerned. And honestly, if I had hair like that, I'd be in a totally different line of work than this. The actor model has been around for a very long time. The original actor model white paper is only a couple of years younger than the original relational database white paper. It originated from a time in the early 70s when computer scientists thought the way computer architectures were going to evolve were these big machines with thousands of cores built into them. And we needed to have some way of designing applications where we could take advantage of all of those. But thanks to Moore's law, that type of architecture never happened. We were able to build very fast computers with a relatively small number of cores instead. So the actor model kind of just stayed in obscurity for a long time until in the 1980s when Ericsson needed to develop the first digital telephone exchanges. They needed to go ahead and come up with some reliable way of being able to scale their infrastructure in more populated areas and being able to handle all the different failures and concurrent concerns that system could have. And what was the byproduct of that was the Erlang language, which was the first real commercial wide-scale implementation of the actor model. And eventually Erlang was made open source, and there's a lot of applications and technologies built on it today. If you've ever used WhatsApp, the core of that all runs on a big Erlang runtime. So even though it's treated as somewhat of a niche language, its ideas are deeply felt throughout the programming community. And actor model implementations like Akka and Akka.net borrow a lot of the concepts from Erlang and make them available on general purpose virtual machines like the JVM and the CLR. So the core concepts of the actor model in terms of what actually makes it effective for use in these distributed systems are the following. First is that you could think of every single actor as a fundamental unit of work and concurrency in your system. All communication is done via a message passing technique with actors, which allows for things like location transparency. Actors can be communicating across the network. They can be running on different threads and communicating with each other. That's semantically, it doesn't look all that different to you as the end user of the technology. Next is that messages are immutable. So the implication of this is, if you're operating, let's say, an actor system within one process, I can go and broadcast one message to 1,000 actors. Every one of those actors can make a modification to that message if they want, change a property, etc. And because those messages are immutable, all those modifications are done locally. So for the .NET developers in the room, what's an instance of a built-in object in .NET that's immutable? String, exactly right. Anytime you go and modify a string, you're not actually modifying the original string you got. What you're doing, in effect, is creating a new copy, making your modification to that, and returning the new copy instead. So immutability helps create some safety, and I'll get into a little bit more detail on that in a moment. Now, the last bit about the actors is that message passing is always asynchronous and decoupled. So, in essence, when one actor tells another actor a message, you're not sitting there waiting for that actor to process that message. That processing will be done offline when that actor has an opportunity to process the contents of its mailbox. And you can think of the mailbox as a little synchronized queue the actor's going to process. Now, speaking of which, what actors can fundamentally do is their primary function is to process messages. They can also spawn other actors. So if I'm a parent actor and I'm responsible for some big domain, so for instance, we have a lot of customers in finance who use the actor model for managing things like real-time financial analytics or processing trades, etc. They might go ahead and have a parent actor spawn a child for each account that's under management. And each account actor might keep track of its own balances, credits, debits, and so forth. The other thing we can do is we can change behavior between messages. So a good example of when you might want to use this. If I was building a chat service with actors, that's something that's be very easy to express. I might have one actor that represents each end user in the system, and that actor might process the same 3 messages for, one message might be joining a chat room, another might be sending a message to a chat room, and then another might be receiving a message in the chat room. The way I process that message might differ depending on the end user's permissions. Maybe they're not allowed into a private chat room. or on the state of their authentication. Maybe this user hasn't logged in yet and they're anonymous. Therefore, before they log in, I might go ahead and buffer all those messages and store them and not send them to the end user. Because you don't want to send a user content they don't have any access to, right? Don't want to send it their way. But then after the user logs in, I might allow those messages to pass through and be displayed on the end user's interface. That's an example of where behavior switching can provide some value. The last thing actors can do is they can contain private state. And what that looks like in Akka.NET is these are just private fields inside your actor class. Nothing more complicated than that. Now, the next thing about actors that's important is what do they guarantee? What are the promises they make to the end user? The first and probably most important promise is that actors process one message at a time. So if all of our messages are immutable, and actors can only process one message at a time, what this means is that anything an actor does while it's processing a message is automatically thread safe by default, because there can't be any side effects, and the actor's state can't be modified concurrently. Therefore, there's no need for an actor to use locks, monitors, or anything else inside its internal sort of message processing area. So this is what we mean when we say actors are a fundamental unit of concurrency. They act as a serializer, in effect, processing things one at a time. Now, next is that messages are processed in first in, first out order, otherwise known as the order in which they're received. So your oldest messages get processed first. So what this allows you to do is if you have one actor communicating with another, if I want to go ahead and have it process a sequence of commands in a particular order, all I have to do to guarantee that is send the messages in that order as well. And the actor will go and do it. Next guarantee is that actors promise at most once delivery. So this is the message guarantee between two actors. If I go ahead and send a message from actor A to actor B, I guarantee that message will be delivered between 0 and 1 times. Now, why would I make a guarantee like that? That guarantee is also known as best effort, which seems like a misnomer to me. I'd probably call that least effort delivery. But the reason why we promise that is because it's stateless. It requires no state to keep track of that delivery because no one's really accounting for it. Now, when actors are delivering messages to each other in memory, it's no problem, because the only thing that could cause a message to be not delivered is the actor being killed in the first place, or running out of system memory, in which case you have a bigger problem. The last bit is that all actors globally have a unique address. So within one network address space, you could have 1 billion actors, and each one will have its own globally accessible URI. But the way you typically communicate through actors is through what's known as an actor reference. It's like a handle to an actor. Kind of like whenever you're writing to a file, you have a handle to that file. You're not actually talking to the underlying disk and trying to get a descriptor back and doing all this stuff. You have a little handle you can use that represents it. So these are sort of the fundamental guarantees of actors under the sort of Erlang/Akka programming model. And Akka.NET is simply this concept implemented for .NET developers. Now, Akka consists of a number of different capabilities. There's the core actor library, which gives you your units of work and the sort of API for defining actors. But Akka is designed to be inherently extensible. The core Akka.NET library is only a couple hundred kilobytes in size. So we have people who embed it into Xamarin and Unity 3D applications. But it also could scale up to support large backend applications, which is what we're here to talk about today. So there's a list of different libraries here that introduce new pieces of functionality, like Akka.Remote allows actors in multiple processes to communicate. Akka.Cluster, which is able to form a topology of those different actor processes together. Akka.Persistence, which gives actors the ability to event source their state to a durable store, like a database like Cassandra, or a file system, or something like Azure Blob or table storage if you want. Then we have a couple of other modules for doing things like introducing additional bits of functionality on top of Akka.Cluster, Akka Streams, which is a whole subject unto itself that I could do a 2-hour talk on if I wanted. But it's a very rich library that can be composed, and you can use as little or as much of it as you want. There are some folks who use just the core Akka library for managing things like concurrent UI updates on a WebSocket application. And then there are others who go and build large clusters with hundreds of nodes in it. So you can sort of take it, you can scale up or scale down very elegantly, which is one of the things that got me into Akka in the first place. Now, this is what an actor looks like. I know the resolution's a little fuzzy, so bear with me here. There's different actor base classes you can inherit from in Akka. And this one is sort of the most basic. It's called the untyped actor. And you have a couple of methods you can fill in. The only method you absolutely have to fill in is this onReceive method, where you receive a message, and then you do some processing. And that's it. The processing doesn't have to be all that intricate. It could be simply inspecting the properties of some message and then sending a message back to another actor, or writing a piece of data to a database, or maybe putting a message into another system like a message bus. Anything you want, really. But then actors also have some other lifecycle methods you can tap into, such as the pre-start method, which allows you to basically have some initialization code that starts, or the pre-restart method, which is an instruction that an actor will execute before it gets restarted, which is a fun capability we're going to talk about. So actors are simple, and they're designed to sort of be, at least in Akka and Akka.NET, not that huge of a leap from object-oriented programming. So quick show of hands, how many developers in the room are doing pure functional programming right now? F#, closure, nope. Good, we're in the right room again. I wouldn't want to do a talk with F# developers anyway. So I'm just kidding, I've got nothing against them. Actors are designed to be simple and give you access to these concurrent, stateful programming concepts. And so the first thing we're taking a look at is state inside an actor is not intrinsically complicated. Like I said before, it's just private fields, like how you define on any other type of object in .NET. And so in this case, this is a read-only property that's set inside the constructor of this actor, but you can have mutable properties as well that you modify as you're processing messages. So the key thing to bear in mind is that that state, though, is never accessed directly through a property or modified. Because the only way to talk to actors is through an actor reference like this, no one else can go and access any of these properties from the outside. The only way actors can share state with each other is through passing messages. So if I want to share a copy of my internal state, let's say we're one of those account actors from our finance example. If I want to share my account balance, I'm going to package that into an immutable message and send that to whoever requested it. And if the requester does something with that immutable message, like modifies it or sums it or does something else, that's going to have no impact on my state at all, no side effects. So that's how state is shared in the actor model. Now, actually, one more thing on this. So the consequence of that, by the way, is what I referred to earlier, which is that all actor state is inherently thread safe. I can share my state with other actors through messages, and they're not going to be able to go and modify it, because the message itself is immutable, and any modifications made to that message will result in that state being locally copied and taken away from there. Now, in terms of actually sitting down and designing an Akka-based application, the way to think about how your actors are actually organized is as sort of a family tree structure, a hierarchy. In Akka and Akka.NET, we have this root actor called user here. This sort of represents the anchor point for all of your user-defined actors. So any top-level actor, which are the actors you declare sort of at the very beginning of starting up your actor system, all exist as the children of this user actor. So if I'm building my finance application, I might have an accounts actor here. Then I might have a grandchild that represents a specific account. Then we might have another top-level actor that does auditing. That might be what its job is. And then maybe another top-level actor that does some sort of utility function, like maybe it flushes changes to the database, something like that. There's no real sort of one true way to go and design any of these actors. But they tend to sort of follow this hierarchical model, where this actor at the top of the hierarchy owns that domain. All of its children are considered to be part of that domain as well. And you can go ahead and recursively model complex entities and complex business processes by just going and breaking apart that domain into smaller and smaller bits. And one of the other popular trends in .NET development right now is domain-driven design. Quick show of hands, who's familiar with that? Okay, good. Well, the idea of aggregate roots is what the parents are in essence. They're the aggregate root for all the different little instances of entities that belong in that domain. And then each little child actor is a bounded context, usually limited to the scope of one entity or maybe one kind of entity. So the further you go down the actor hierarchy, the smaller and smaller the context of that actor gets. Following me so far? Good. Now, this is not what this slide looks like on Windows, so I apologize here. My taste in colors is usually a lot better than this. So what I'm trying to illustrate here is how actors process messages. Typically, you have your actor class here. So this is your sort of actor class implementation that you programmed yourself. That's what this little black blob is down here. This other black blob is your mailbox. Your mailbox is sort of a construct that you don't usually interact with directly as an Akka end user. You can do things like customize its implementation and so forth, but typically the default mailbox is usually what you end up going with. And what happens is, this actor will be woken up to begin processing messages in its mailbox one at a time. So the first message at the front of the mailbox, the oldest message, gets pushed into that actor's onReceive method. And until the onReceive method exits, we're not going to begin processing the second message. So now, as we go ahead and work through the contents of our mailbox, we'll go ahead and basically receive the next message at the front of the queue and so forth. And this actor will continue doing this until either it's exhausted all the messages in its mailbox, or in Akka we have this concept of dispatcher throughput, which basically specifies an actor can only process a burst of messages this size before yielding to another actor. And the reason for that is that actors share threads. So, I'd love to tell you that the actor model is magical, like quantum computing, and we don't have to use, shoot, I'm blanking on the name of the type of operating system now. But we don't have to use sort of traditional programming constructs like threads and etc. But the truth is, under the hood, actors are using threads and sharing them together. And the way this typically looks, if we have a two-core machine, is we'll have a pair of actors that received messages first at the front of our dispatcher queue, and other actors behind it who will begin processing messages. Now, once these two actors are finished processing a batch of, let's say, up to 30 messages each, the next actors behind them will go ahead and be scheduled for execution. And one of these actors, like A1, can appear again on the dispatcher to basically be scheduled for execution again after these other actors have run. If you have one actor that receives a particularly large number of messages, it'll be reappearing on the dispatcher queue all the time. And what this helps us do, in essence, is you can have millions of actors, but only in one process, but only a relatively small number of them are actively processing messages at any given time. When an actor doesn't have any messages to process, it doesn't use any CPU. It'll sit there resident in memory, but it's not going to be actively using any of your threads or other CPU resources unless it has a message to process. So actors are lazy by default. I usually have a slide of a mailman sleeping inside a mailbox when I introduce that, but I think I omitted it from this presentation. I'm sorry for disappointing you there. Now, this is sort of what I've described thus far is how actors work within one process. But what we're really interested in is what can we do to go ahead and build a networked system with actors? How does that work? Well, the most important thing about actors on the network, in my opinion, is actually the fact that they're using messages to communicate, as this is what gives us the potential for distributing them across a system in a transparent way in the first place. So most of the way we've been taught how to program from a pretty early age when we first start doing hello world style applications is we think about method invocation. And when you're building web APIs or RPC systems, all you're doing is really taking that invocation concept and translating it over the network. So when I call a web method, I'm waiting for it to send me a response back before I move on to the next part of whatever my work is. With messages, we have a lot more paradigms we can work with for how we want to have our systems communicate and interact. So the first thing to bear in mind about message-oriented programming is that our messages are comprised of two parts: a payload, which describes our data, and then a reply-to address, which can be null, could be empty. But that describes who should be notified when we're done using this data, or who needs to be notified about the next stage in processing this information. So usually a message comprises of those two parts. So these gradients I created aren't turning out all that well. The next thing about message processing is that it's always done asynchronously. You can, if you want to, force it to be synchronous, but the default nature of it is always asynchronous. Whereas with method invocation, it's the other way around. Method invocation is synchronous by default. So that's sort of a 180-degree difference there. Another big benefit of messages is that they can be serialized and stored. By virtue of transmitting a message over the network, you already have to serialize it. Well, what are some other things you can do with a serialized message? You can persist it, right? You can go ahead, and so that's one of the things that Persistence does. It gives us the ability to represent an actor's state as a series of persisted serialized messages stored in a database or a file system somewhere. Another big advantage of messages is you can mutate the order in which you process them. So when you receive an invocation, if you're doing traditional procedural programming, you have to respond to it. You can't go and forward that method call to another process running somewhere else in the network. And you can't necessarily defer it. That's sort of the synchronous model of how method invocation works. Well, with message passing, I can defer a message if I want. I can defer processing on it until I'm ready. Or I can delegate processing of it to another actor or to another process somewhere. Yeah, and you can also forward a copy of that message if you want. And you can also do broadcast and multicast messages, where multiple parties can all respond to the same command simultaneously. So the picture I'm trying to paint for you here is that with these message-based programming models, just even without actors in the picture yet, even if you're using something like a message bus, you already get much more flexible modes of communication and interactivity than you would get with a traditional method invocation or RPC model. And messaging patterns can be quite powerful. So first, we'll take the one that we ended with. You can do a broadcast pattern, where one node can broadcast a command to many other nodes. You might see this in systems where you want to go ahead and issue some sort of immediate instruction that you want the cluster to process all at once. So for instance, we have some customers in IoT who need to be able to send control signals to devices when there's an emergency. So I might want to send an emergency stop command to all nodes. Or I might want to send an emergency reset command to nodes that are affected with a certain issue. Broadcast is a pretty simple pattern for doing that. Proxy is another type of pattern where I can go ahead and receive a message and forward it down to another node, and that node can be the one that actually does the concrete work and reply back. This can be really useful in scenarios where maybe I don't have the right piece of state to deal with this request directly, but I know who does. And I can forward the message on to that party and do it. Pub/sub is another really popular messaging pattern with actors and message-based systems. Multiple nodes can go ahead and let a publisher know that they're interested in certain topics that publisher might be aware of. And one of those messages arrives, we can broadcast that back out to all the other nodes in the network and have them begin processing it. Then you can also do one-way messaging, which you can think of like calling a void method. You're not going to get any return back at all, but some work is going to be done on the other side of that message. Now, I'm using the word node here somewhat loosely. In the actor model, these can all be individual actors, even running within one process or running across the network in multiple processes if you wish. The purpose of sort of surfacing this information now is that the communication models you can achieve with actors and with message-oriented programming are inherently much more flexible and capable of adapting to changes in network conditions, to changes in available state, and so forth. And what you can use with these messaging patterns is you can compose them together into protocols that describe rich pieces of functionality inside your application. And this is how we can start reasoning about things like network failure and partitions. So for instance, this is an example of what a simple consensus protocol might look like. We have a write that comes into one node on the network, this little replica here. And we want to go ahead and have the effect of that write replicated across a couple of other nodes for redundancy or maybe availability purposes. Well, the next stage of our protocol will involve checking with those nodes to see, are we in a state where we can accept this write? Is this write a valid, describing a valid transition to the next state according to our business rules? If that write is valid, we'll receive an acknowledgement back, and then we can go ahead and perform a commit. And then if you really wanted to make this a sort of legal transaction, you'd probably have another set of acknowledgements come back in verifying that the commit went through. Now this is an abstract example, but things we can describe when we're building a protocol like this would be, what should we do if we never get a response back from one of these nodes that we're talking to? Well, if you want to build a system that's consistent, the right thing to do is not commit the transaction, right? Because we can't guarantee that this node is in a state where we can do it. So maybe we go ahead and simply fail the transaction and let the end user know to retry again. Or maybe if we have a little bit more flexibility with how consistent our state needs to be at any given time, we go ahead and do it anyway and let the chips fall where they may. Maybe we'll have a write conflict or a stale read, but that might be permissible under our current set of business rules. So the idea is with messages, you can go ahead and construct these types of flows and behaviors throughout your system and include the opportunity to handle failures and partitions and treat them as sort of a normal business concern, not some exceptional emergency that you have to be woken up at 3 a.m. to solve. Now, the next piece of the puzzle here, messages are one part of what makes it easy to build a distributed system with actors. But the ingredient that Akka includes is the notion of an actor reference, a handle directly to an actor. I have 5 minutes? All right. An actor reference gives you an ability to go ahead and communicate with an actor anywhere in a local process or anywhere over a network. As the end user of Akka, you don't necessarily need to know whether or not this actor is local or remote in order to work with it. You design your protocol to work in a manner where this actor may be remote, therefore we need to anticipate all the different types of failure classes that can occur, or it may be local. Either way, we design a protocol that's sort of consistent with what we'd expect in a distributed system, and these actor references will hide whether the actor is local or remote. This little actor reference we get back when we start an actor here could be a local actor reference or a remote actor reference. And it doesn't really matter that much to you as the end user. Now, I guess the concept I'll end with here, so we can take some time for questions, is the notion of location transparency is sort of paramount to the way Akka and Akka.NET and Erlang are all intended to work. An example of something that has location transparency you use every day is your phone number. If I want to call one of my engineers on my team, Nick, who's on the East Coast of the United States, I don't have to tell AT&T how to route my voice packets from Malaga all the way to Maryland, where he lives. My phone, just by virtue of punching in his phone number with the country code, AT&T and Vodafone's network will figure that out for me automatically. Another example of something that has location transparency is the domain name system. Imagine a parallel universe, harkening back to quantum computing here, where you have to keep a yellow sticky note taped to your monitor with all of Google's IP addresses. And you need to know how to go ahead and manually ping those if you want to use their service. The DNS system kind of hides the physical location of all those servers, so you just need to know their logical address instead, which is the domain. Actors give that to us. In essence, these can all be different actors who are passing messages back and forth. And I don't necessarily need to know whether this actor is on one node and this actor is on another. You don't particularly need to care under the sort of design of the actor model. Now, where all this sort of comes back home to where I began this presentation with talking about industry trends and needing to build applications that can scale, is when we start thinking about what's the role that state plays in our system. In those previous designs that we saw, state was outsourced in its entirety to the database. That's sort of a CRUD architecture. Well, if I need to build a real-time stream processing application where I'm processing a stream of user events and serving ads or sending messages back and forth, I might need to go ahead and change the way my application is designed with regard to where state lives. So question for everyone who's attending. Assuming these two architectures have access to the same exact data, which one will be faster? The stateless one on the left or the stateful one on the right? The stateful one. The stateful one's able to take advantage of a principle known as state locality, which means that the information you need to do your work is local in process to the code that does the work. So instead of having to receive a request, serialize it, turn it into a database query, let the database query run, fetch the results from disk, serialize that, send that, etc., I can just go and check an adjacent register in memory and get the data I need that way. This will be multiple orders of magnitude faster, but it comes with a cost. Let me just step through this here since we're short on time. State makes protocols work. Here we go. This is what I want to get to. The cost of having to keep state in memory is that state has to be managed in a consistent manner in order for it to be useful. If we go ahead and treat our state willy-nilly, we'll get unpredictable results and may not necessarily have an application that behaves all that well. So the CAP theorem is sort of the fundamental trade-off framework that we use for describing how these systems should treat their state and what are the different rules we need to go ahead and sufficiently protect it. So in general, I tend to think of the CAP theorem as a gradient, where you have three different currencies you can trade: consistency, availability, and partition tolerance. Consistency refers to the property of all nodes seeing the same data at the same time. So if I have two nodes that are supposed to be replicas of each other, my consistency can be measured by how quickly does it take one node to be aware of changes occurring on another node. The shorter the time frame between those two differences, the more consistent your system is. If those nodes take a very long time to synchronize with each other, they might be consistent eventually, but there's going to be a long window of time where they're not. They'll be inconsistent. The next property is availability. And this is a guarantee that every request receives an explicit successful response. Anyone could write a system that could serve back 500 errors quickly. Our state governments do that all the time. But being able to guarantee that every request can be successfully processed will come at a price where you might have to trade away some consistency in order to do it. And then there's partition tolerance, which is a guarantee that the system is able to continue despite arbitrary partitioning due to network failure. So for instance, in those previous diagrams I did, sort of the internal, sort of a private zone of an enterprise architecture, if we lost the ability to communicate with SQL Server, we wouldn't necessarily be able to tolerate that partition, and we would go down. So the last thing I'll end with here a little bit. 40 client has been updated. That's good to know. Last thing I'll end with here a little bit is we have a protocol on the top and a protocol on the bottom for dealing with writes in a distributed system. Is this design more consistent than this one on the bottom, where I have to establish some agreement amongst our nodes? Yes or no? Well, the answer is, this design on the top is more consistent because we're forcing the nodes to agree on what the next state should be at the time we're doing the write. So if there are any conflicts, we're going to go ahead and choose to be unavailable and reject a request that we can't process because that next state transition might be illegal. On the bottom down here, we're choosing to go the more available but less consistent model, where this node might accept a write right away, but we don't necessarily know if there's another write on this server that might be conflicting with it. And so I didn't get a chance to go through all my slides here, but I'll go ahead and take some questions in a moment. The bottom line I wanted to address is that what the actor model gives you is all these abstract concepts in distributed programming can seem very unrelatable and difficult to access. The actor model gives us the tools to begin reasoning about them in a manner that is easy to ramp up on, because you can start by doing everything within one local process if you wish. And you can translate those concepts over to the network relatively frictionlessly. So that being said, I'd be happy to take some questions, and thank you very much for attending my talk today. All right, who's first? Go ahead.
If I understood correctly, you will have like one actor per data element or per data row or something in the model to keep its state?
Yeah, typically what you'd want to do is have one actor be responsible for the state of any given entity. One of the modules that I didn't give a lot of lip service to is cluster sharding, which does this sort of as a service, where each entity, let's say I have 10 million bank accounts I have to keep track of. Each one of those bank accounts would have its own actor with its own state. And depending on how complex the state of that entity is, maybe that bank account actor would also have children that represent different parts of its state potentially as well. So,
how is then memory management, etc. done? Because you can't have all data always in memory.
Oh no, of course not. What you would do is that actor would go ahead and do something like, we have a concept in Akka called receive timeouts, which is when an actor has been idle for longer than a certain period of time, you receive a message indicating that I haven't received a message in 60 seconds. At that point, that actor would go ahead and self-terminate, and all of its state, it would flush to a database or something. So that way, the actors that are active are only the ones that are doing work at any given time. So like in my marketing automation system that I built originally with Akka.net, we would have at any given time 500,000 actors per node processing work, but at any given minute, those 500,000 actors would be a different 500,000 actors than the one we had before. Does that make sense?
Cool, thank you.
You're welcome.
So in terms of scale, would be the same number of actors in every node?
Not necessarily, because you can have multiple nodes with different services implemented. So you might have like a web front-end node that has a very small number of actors whose only job it is to push data into like a stateful service somewhere, right? And that stateful service node might have 1 million actors in each process. Ideally, you'd want a relatively even distribution of work across all of those nodes in order to avoid running into an issue where you have a hotspot somewhere. So yeah.
We're probably going to have to wrap it up there. Okay, one more question, and then
I'll be fast.
It's obvious that the actor model successfully deals with the distributed transactions. So I'm wondering, what about the MSDTC? Does it need to be up and running?
I've never worked with MSDTC, so that'd be maybe a Sergey question and back. We have the founder of Orleans behind us there. But no, I've really never done much work with actual distributed transactions or anything in the sense of like using the DTC coordinator to go and do that. So most of what I've worked with is much more like all changes for one entity go through exactly one actor. Therefore, there's real no need for coordination. And I'll talk to you a little bit offline perhaps, so I don't block Roland from coming up and giving his talk about some of the distributed state management stuff that we have available in Akka. All right, thank you for your questions. Appreciate it.